This is the solution to homework set number 3 for ECE 321. The first problem is I've got a thermistor. This is similar to the ones up in room 211. It has a resistance that varies with temperature. I'd like to take that thermistor and convert it to a voltage using voltage divider with a 2K resistor. Now, given the voltage, determine the temperature based upon voltage measurements. Again, the idea is I can measure voltage with a voltmeter. From that, deduce what the temperature is. One way to start is to use MATLAB as temperature goes between 0 and 30 degrees Celsius. Calculate the resistance, and here I added 273 because the equation for the thermistor used Kelvin rather than Celsius. Find the voltage using a voltage divider, and now let's do a least squares curve fit. The voltage versus temperature is the blue line. It's got a little bit of bend to it. If I want to do a least squares curve fit, I pick the basis. Here the basis is voltage in 1. Solve for the constants, so that says temperature, right here, is minus 8 times the first basis vector, minus 8 times v plus 54, gives you this negative correlation. That's my linear curve fit for voltage versus temperature. So now if I can measure voltage, I can tell you what the temperature is based upon that linear curve fit. There's a little bit of difference in the two. That's the error. The error is occasionally 1 degree low or 0.4 degrees high. So there's the error in the linear curve fit. Problem 2 says let's use a cubic curve fit. All you have to do here is change the basis function to have a cubic function. Now do your least squares just like we did before. The first number is times the first basis element. This is minus 0.14 v cubed. The second answer is times the second basis element, 2.47 v squared, minus 21v plus 75. If I do that, I now get a curve fit which is much closer. It's only off by 0.03 degrees Celsius. So given a voltage measurement, I can tell you temperature. That's the idea behind calibration. Come up with a function where you take something that you know, say the voltage, to determine something that I want to know, like temperature. And the number of terms you include depends upon how much accuracy you want. If I want to be within 1 degree, linear curve fit's fine. If I want to be within 0.03 degrees, a cubic curve fit's better. Problem 3 looks at filters. If I have the following filter relating x and y, this represents a differential equation. Cross multiply, and in Laplace, s means derivative. So what this means is the second derivative of y plus 11 times the first derivative plus 24y is 30x. So this is the differential equation that filter corresponds to. Where filters are nice is suppose I have a sine wave input, like problem B. If I have this, I use superposition. If the input is a constant, then x is equal to 5. My frequency is 0, so this is the gain everywhere. Find the gain at s equals 0 times the input, I get 6.25. So at DC, the output is 6.25. Repeat, if the input is 6 cosine 4t, now s is j4, the frequency of the cosine. X is 6 plus j0, 6 cosine plus 0 sine. This is the gain everywhere. Find the gain at s equals j4 times your input, I get a complex number. Here the complex number means the real part's cosine minus j is sine. Put the two together, I get the total answer. Note one mistake people often make is they'll add these two answers together. They don't add. The 6.25 is the DC. The 0.7 is at 4 radians per second. This doesn't simplify. You can't add the two complex numbers. Problem 4 looks at designing a filter. In next homework assignment, we'll be designing a Butterworth or Chebyshev filter. With fmin search in MATLAB, I don't need to know anything about filter design. I can let fmin search design it for me. So here what I want to do is come up with a filter of this form. This is as close as possible to an ideal low-pass filter with a corner at 6 radians per second. If I let MATLAB search, it'll sit there guess again, and eventually winds up with this answer. And the numbers it spits back are the 181, 3.27. That corresponds to these numbers. There's the 181, 3.27, 7.06. Where that comes from is the cost function I used was this one. I'm going to pass a z, that's a vector. MATLAB is a vector language or matrix language. The matrix z contains 5 terms, and what that means is that's my a, b, c, d, e. Given those, throw that into your transfer function. A is the numerator, B, C, D, E tell me the denominator, the actual gain versus frequency is numerator over denominator. This is what I want the gain to be. The error is the difference in the gains, return the sum squared error, and let fmin search minimize j. And what it did is it came up with, this is my minimum. The sum squared error is 1.9. That's the smallest it could make the error with these numbers, which gives me the red line. That's the actual gain versus frequency. The blue line is what I want it to be. And take the difference of the two, that's the error. Add up the sum squared error. The smallest MATLAB could make that was 1.93. So that's filter design using MATLAB and fmin search. To implement the filter, what you do is you split this up into two parts. Here's one set of complex poles, here's the other set. It works a little bit better in polar form. So take this pole, factor it. This is a pole at 2.65 at 52 degrees. This one is a pole at 5.23 at 83 degrees. To implement the circuit then, one over RC is the amplitude. Here 1 over RC is 2.65. The gain right here sets the angle. The angle is 52 degrees, so K is 1.76, and the gain is 1 plus the resistor ratio. So this is 0.76 to 1. On the second stage, the amplitude is 5.23, that's 1 over RC. The angle is 83 degrees, so 3 minus K is 2 times the cosine of the angle. I want a gain of 2.76, meaning this is 1.76 to 1. This circuit should implement that filter. Note that the DC gain is wrong. For the filters, this circuit provides a gain of 4.58 instead of what it should be, instead of DC gain of 1. The easiest way to handle that is to say the output is 4.58 times Y. Presumably there will be some other stages adding gain to your amplifier. This circuit provides a gain of 4.58. The rest of the gain is added somewhere else. So that's my circuit to implement my filter. To test in Circuit Lab, I can build the circuit like this and then do a frequency sweep. I'm going to sweep V1 and plot linear voltage versus frequency. And this is the same thing we saw in the previous graph. The gain starts out, I have the first resonance, second resonance, then drops off. What that tells me is the circuit that I implemented has this frequency response. That's the same thing as I got in MATLAB right here. So I implemented the circuit correctly. That's homework set number 3 for ECE 321.